Welcome back. Let's continue our discussion on linear regression. This is part 2. A quick recap of what we saw last time. Last time we said that linear regression was basically an attempt to create a linear model in the sense where the output was modeled as a linear combination of the inputs. In other words, the dependent variable was modeled as a linear combination of the independent variables. Right? What did we have? We had a whole bunch of training data. Right? The training data essentially comprised these vectors x1, x2, x3 and so on. Okay, let's say we had m points in our training data, and each of these vectors x1, x2, x3, etc. Contained elements which were the values of the independent variables, right? And we put a 1 right in front because w0 is multiplied by 1, right? So x1, x2, x3, xm were the points of the training data, the inputs corresponding to points in the training data, and each of them was a vector whose values were the values of the independent variables. Corresponding to each of these inputs in the training data, there was an output, an observed output, right? So y1 hat was observed when the inputs were x1, y2 hat was observed when the inputs were x2, and so on and so forth, right? What we tried to do was create a linear model. That means we tried to express the output y as a linear combination in the sense w1 was multiplied with x1 was multiplied with w1, x2 multiplied with w2, so on and so forth, wn xn plus w0. We wrote this linear equation, okay, and our job in solving the linear regression problem or creating the linear model was to choose these values of w1, w2, w3, etc. so that the output y was as close to the observed output as possible for the training data, right? So in this model, if you feed x1, you will compute a y1. If you feed in x2, you would compute a y2, and so on and so forth. And the objective was to select the values of w1, w2, w3 till w0 so that y1 and y1 hat were as close as possible, y2 hat was as close as possible, and so on and so forth, right? So these two were as close as possible. That was what was meant by finding the best W and the best linear model. Okay. We defined the square error as the metric that we wanted to minimize, and the square error was essentially y1 hat minus y1 squared plus y2 hat minus y2 squared, and so on and so forth. We found the difference between the observed and the computed, squared it up and added it over all the training data, and that was the metric that we wanted to minimize. In the vector matrix notation, which we sort of utilized last time almost exclusively, y, the output, was w transpose x, where x was this vector, input vector, and w was the vector of the weights. So w is the vector that has its elements w0, w1, w3, and so on and so forth, right? So this was the linear regression problem that we saw last time. We went about minimizing the mean square error that I talked about, and we came up with solutions in two different ways, right? So there were two ways of solving the linear regression problem. One way of solving the linear regression problem was to, of course, use what is known as the closed form solution, where we explicitly came up with the answer that this is what W was going to be. X transpose X inverse times X transpose Y hat, where Y hat was the vector of observations, right? So this is the closed form solution for the best W. And just to remind ourselves, X was this big matrix right here, right? So this was X. Okay. This was a M by N matrix where M is the number of points in the training set and N is the number of independent variables, right? So this is what the closed form solution was. The other solution that we sort of came up with was the gradient descent solution. Okay, and why did we come up with it? We noticed that the closed form solution involved a matrix inverse. You had a matrix X transpose X whose inverse you had to find, and this was a matrix of size n plus 1 by n plus 1. And if n was large, if the number of independent variables was large, inverting this matrix would generally become difficult, and therefore we came up with another solution which was essentially an iterative solution, and we used the gradient descent mechanism to come up with this solution. This solution told us that in each iteration W new was simply going to be W old minus this quantity, where this x we already saw what it was, and y minus y hat was the vector of residues. So this solution did not involve a matrix inversion, and therefore it was less computationally intensive. Of course it was iterative, so you had to kind of go over multiple iterations. But these were the two ways of solving the linear regression problem which we saw last time. Okay, now when we looked at binary linear classification, we used the gradient descent approach there as well, and we also talked about something called the stochastic gradient approach, which was as we said, a clever trick to essentially reduce the computational load involved in gradient descent. Okay, and what the stochastic gradient mechanism said was that instead of essentially averaging over all the training points to get the direction in which to move in, you would use one random training point for every iteration. Okay, so remember, what we do in the gradient descent is, in order to find the best direction to move in, you perform a operation over all the training points, right? So over the entire training set, you find the direction to move in for each point, average it out, and then move in that direction, right? As opposed to that, in stochastic gradient, what you do is, in every iteration you take any one random training point, okay, and move in the direction defined by that training point, right? And then you hope that the averages sort of work themselves out over all the iterations. So instead of taking the average over all training points in each iteration, what you do is, for each iteration you use a different random training point, and imagine that things will basically average themselves out because you are going to select a different random training point for every iteration, right? So in vector matrix the scenario, you were sort of, you had this big matrix X. In stochastic gradient, you are just going to use any one randomly selected point in the training data, right? And therefore your iteration becomes W new equal to W old minus just this, right? Because your X matrix is no longer a matrix, but just any one randomly chosen row out of this matrix X. You have this X is a vector now, and YR minus YR hat, basically the Y corresponding to that row, the observed and the computed, this is basically a scalar. So you are multiplying a scalar with a vector. There is no vector matrix multiplication, and you get the new W in each iteration. So just to contrast with what we were doing in the generic gradient descent, in the generic gradient descent, this was a matrix of size m by n, which was being multiplied with a vector, the vector of residues, and this was happening in every iteration. As opposed to that, in stochastic gradient, because you select one random point in each iteration, you essentially do not have a vector matrix notation. this matrix reduces to a vector and this vector reduces it to a scalar. So you are just multiplying a scalar with a vector. I suppose we should put a R over here to indicate that it's the random X used, right? So this is what the stochastic gradient was. And you know, pictorially, you essentially is the same thing. You begin at a point and move in a direction defined by the gradient for that point and keep moving till you essentially hit the minima, right? Now in stochastic gradient, as you can imagine, you would have many more iterations, but the computational burden in each iteration would be substantially less, and therefore this is a more efficient way of going about solving the gradient descent. Right, so this is the stochastic gradient, and the reason I sort of mentioned it here is to show you how it works in the vector matrix notation which we have been using exclusively. The stochastic gradient algorithm just becomes, you know, like a vector multiplied with a scalar in each iteration. And then there was the batch gradient, which was exactly what we also saw in the case of the binary linear classifier. Here, you know, you do not take a single row. You instead take few randomly defined rows in every iteration. So the XS is a subset matrix, or rather it's a matrix that results from taking only a few rows of this overall matrix X and then evaluating W new from W old by using this subset matrix which comprises only a few rows of the overall matrix X. So in each iteration you use a different subset of rows. It's a much smaller number compared to the total number of rows in X, and therefore it is sort of a, you know, a compromise between using all the rows as is done in gradient descent and using only one row as is done in the stochastic gradient approach. So this was batch gradient. Okay, so with that out of the way, let us move on. Okay, let us move on. Linear regression applications. Okay, why do we use linear regression? Why do we employ linear regression? There are two answers, and the first answer is, of course, something that we've talked about. Predict the output for unseen inputs, right? So you create a linear model. You create a linear model based on your training data. Okay, so that when confronted with a test input, an input that you have not seen priorly, you can estimate what the output is likely to be. Okay, so once you train the model, once you train your linear model, once you compute the best W's, you use that linear model to predict the output for test inputs. That's one application of linear regression, right? Quite obviously, and this was the motivation for getting started in the first place. But there is also another application of linear regression. Okay, and that is, you often employ linear regression to understand the relative importance of the independent variables. Okay, suppose you have a scenario where you have, let's say, hundreds of independent variables, right, in your model. Let's say you have 200 independent variables, and you build, you sort of run a linear regression. Okay, so your output is a linear combination of those 200 inputs. Right, now it's entirely conceivable that not all the independent variables have significant impact on the output. Right, so it's possible that some independent variables have greater impact on the output than others. Right, and sometimes it is your purpose or your objective is to essentially understand which of these 200 independent variables are the most critical to you, or which have the most impact on your output, and which independent variables are sort of insignificant. Right, so understanding the relative importance of independent variables can be an objective in itself. Right, now how do you do that? Usually what will happen is that the independent variables that are more important or more significant will have W's, will have weights with larger magnitude. Okay, so when you run the regression, when you come up with the best values of W, and if you look at the values of W, the values of W that have highest magnitude, are the parameters, are the independent variables that are most significant to you. Okay, and the ones that have very small values of W are the insignificant ones. Now, when you go about examining the values of W, it's important to keep in mind that the values of X's, the values of the independent variables, basically have, roughly the same order of magnitude. Okay, so or have the similar dynamic range, each of them. So for example, if x3 was, let us say, x3 was measured in kilograms versus grams, clearly W3 would be, the scaled, the ideal W3 would be scaled appropriately, right? I mean, if X3 was in kgs, W3 would be a lot higher. If it was in grams, W3 would be a lot smaller, right? Now, that doesn't mean anything unless you have all the X's in the same dynamic range. So for example, if the values of all the X's lie between, let us say, 0 and 100, let's say, I mean, you use units for each of the independent variables so that they all lie between, let's say, 10 and 100, right? 0 and 100. That would be okay. But if, let's say, X1 took values in hundreds of thousands and X2 took values in fractions, clearly you would not be able to just, do a straight comparison between the magnitude of W1 and W2. That's what I meant. So select, if item number 2 is your goal, if you want to understand the relative importance of the independent variables, if that's the reason why you are running a regression, make sure that you choose units of X1, X2, X3 and so on, such that the numerical quantities X1, X2, X3 in your training data have a similar dynamic range. Okay, they look numerically, they are around the same order of magnitude. So this is, this is the second reason why people may run linear regression. Okay. As we go about looking at various techniques in AI, we need to know sort of, we need concepts from different subjects. In a way, you need to know a little bit of calculus, you need to know a little bit of linear algebra, vector matrix computations. You need to, and because AI deals with a lot of data, you also need some background in statistical tools. Okay, and as I mentioned last time, this lecture is going to focus on measurements, and we are also going to be talking about data assumptions. Some of these statistical tools are going to become important. Okay, so what are we going to be doing in the remainder of this session? Firstly, we'll talk about measurements, how we measure the effectiveness or the efficiency of a linear regression model. That's the first thing we are going to talk about. We will also look at data, and we will talk about, what are the circumstances in which a linear regression model works well. Okay, so when does linear regression work well? And thirdly, we will see what sort of pre-processing we can perform to enhance the performance of a linear regression model. So that's going to be more or less our agenda for the remainder of this session. Okay, metrics for measuring accuracy, right? How do we measure the accuracy? I mean, the two things that immediately come to mind is firstly the mean square error. I mean, this was the metric that we used as the optimization metric, right? I mean, we actually when we went about developing the closed form solution or even the gradient descent, this was the quantity that we were seeking to minimize, and therefore the mean square error itself is one metric for measuring the accuracy of your linear regression. And remember, this is happening on the training data. So on the training data, this summation goes from 1 to m. Summation goes from 1 to m, where m is the number of points in the training data. You essentially calculate the sum of the square errors, the error being the difference between the computed y and the observed y, right? So this is one metric for measuring how well your linear regression model is doing. If you don't like taking squares, you could probably work with absolute value of the error. So some mean absolute error, 1 over m summation of the absolute value of the differences, and you basically sum them up over all the training data. That's another metric you could use for measuring accuracy. But there are more sophisticated metrics as well, as you would have guessed. Okay, one metric that is often used to evaluate the efficacy or accuracy of the linear prediction model, the linear regression model, is called the R-square score. Okay, also called the goodness of fit. Okay, and it's a statistical measure of how well the linear regression predicts how well the linear regression predictions approximate the data points. Okay, so now let me sort of, there is a lot on this slide, but let's work through it. Okay, so this is a definition. R-square score is defined as 1 minus SSR divided by SSM. Okay, SSR is the sum of squares of residual errors. This is a quantity that we are familiar with. It is the quantity when divided by m is the mean square error. So this is the square error, y hat I minus yi square. Okay, on the last slide we wrote yi minus y hat square. It's the same thing because there is a square over here. This is the square error, right? So that's the numerator, it goes over here, and the denominator is the sum of squares of differences from mean. Okay, now let's understand what that is. Your y hats were the observed outputs in your training data. Okay, clearly you can average them and come up with an average y hat, right? So you had y hat 1, y hat 2, all the way to y hat m. You add all of them up, divided by m, you come up with the average y hat. And what you do is you subtract this average from the y hats, okay, square it and add it all up together. So it is essentially the sum of the squares of the differences between the yi's and their average. Okay, and that is what goes into the denominator here, SSM. So your R square is basically this. Okay, you can stare at this for a minute. Okay, you can stare at this for a minute and kind of some of the things will pop out, right? So y hat I minus y hat, this numerator is the square error which we have been looking at all the while. The denominator looks pretty similar to this, except that y hat average is actually a constant. It does not depend on I, because it is the average of all the y hat i's. Okay, let's take a graphical example in 2D and see what this is, right? I mean, the black points that you see over here, are your training points, right? Okay, the yellow line that you see here, this yellow line is the average value of y for each of these points. So you add the y coordinate of each of these black points divided by the number of points, so you get the average y, and that's your yellow line. It's naturally flat, it's a constant, right? So this is the average y for all the black dots. The blue line is your linear regression line, the best hyperplane, the best line in 2 dimensions that you found by running the linear regression. Okay. Now, the numerator over here is simply the sum of squares of the reds. Okay. So for each of these points, I have drawn a red dotted line over here, which is the difference in the y of the blue dot and the y value on the blue line, right, for that point. Similarly, for this point, the difference between the observed and the prediction made by linear predictor is this, and so on, right? Okay. So the numerator is the sum of the squares of the reds. Okay. So for this point, this is the red quantity, right? This is the observed y. This is the y given by the linear model, and their difference is what you're going to square and add. So you do this for all the black points, and that's the numerator right here. The denominator is the sum of squares of the greens. Okay. So basically the difference in the y value of this point and the average. Okay. Difference in the y value of this point and the average y. The difference between the y value of this point and the average y, and so on and so forth. Right. So that is what your denominator here is. Right? Sum of the squares of the difference between the observed y and the average. Summation over all the points. Right? And R square score is 1 minus this. 1 minus this. Okay. Let's stare at this for a little while, right? I mean, let's stare at this for a little while, and some things will sort of become obvious. The first thing that you sort of notice is that the maximum value that R can take is 1. Okay, R square score can take is 1, and that happens when this is 0. So if your linear predictor, if your linear regression comes up with a hyperplane or a line in 2D such that all the points fall exactly on that line, right, then the numerator is going to be 0. That's the best you can do, and then your R square score is 1, right? Okay. In general, your numerator over here is going to be smaller than the denominator here. Okay. Why is that? Because you expect your linear regression model to come up with a hyperplane that passes as close to possible as possible to these training points, right? Definitely better than simply taking the average, right? So you would expect that your linear regression results in a hyperplane that does that passes closer to these training points on an average as compared to the flat line that you have here. I mean, if your regression was any good, clearly that would be the case, right? I mean, it may not apply for every point. You may have some points that are closer to this y average as compared to this compared to your regression model. But overall, when you sum over all m, when you sum over all the training points, you would imagine that your linear regression line did a better job than your average line, right? And in other words, these errors summed up over all the training points would result in a quantity which is smaller than this quantity in the denominator, right? That would be your expectation. And in which case the R square score is going to be less than 1, right? Because this will be non-zero, but it will be a quantity that is probably less than 1, and your R square will therefore be 1 minus a quantity that is less than 1, right? Now, let me be very clear. Theoretically, R square can be negative as well. I mean, if your God forbid, I mean, if you sort of drew a line, your linear regression, you made some mistake, I don't know what you did, but you came up with a line right here, the differences between y hat and this line would be greater than the differences between the y hats and the average line, in which case your r square could actually be negative. But that is a pathological case. I mean, this is not what you would expect when you run a a genuine linear regression. This is not likely to happen when you run a linear regression. It is a pathological case where I'm just saying that you come up with some hyperplane which is far away from your training data, in which case over here your numerator becomes greater than the denominator, and therefore r square becomes less than 0. Okay, I mean, theoretically speaking, pathological case, forget about it. Overall, let's remember though that r square in if you're running regression in any serious setting, your r square is going to lie between 0 and 1. Okay, 0 and 1. Okay, now this this r square score has facets to it that we need to sort of convince ourselves of. R square score is the percentage of response variable variation that is explained by the linear model. Okay, so what is the R square score? I mean, in the R square score, what you're really doing is comparing the performance of your linear regression model with your bare bones average, right? I mean, this requires no model. The denominator here requires no model. The numerator here requires a model to sort of ensure that this numerator is as small as possible. Okay, and the R square score therefore sort of is the percentage of the response variable variation that is explained by the linear model. Okay, in other words, it is a measure. It's a measure of how good your linear regression model is, right? How much better than the average y hat is your linear regression model, right? That is what the R square score indicates. It also tells you something else. It also tells you really, I mean, assuming that your linear regression algorithm runs correctly the way it's supposed to be run, without mistakes, the R square score also tells you how much of a linear relationship exists between the observed variables and the independent variables. The observed variable, there is no plural over here. Okay, so that's what the R squared score tells you. It tells you if there is a linear relationship between the observed variable and the independent variable. And why does it tell you that? Because if a linear relationship indeed exists between the observed variable and the independent variables, your regression would come up with a line or a hyperplane that captures that linear regression, that linear relationship, which would result in a small numerator over here, and therefore the value of r square would be closer to 1. So a high value of r square, and by high value I mean, let's say higher than 0.8. Okay, that's a high value of R square score. It tells you that there is a linear relationship between the observed variables and independent variables. If your R square is less than, let's say 0.8, I mean if it's less than 0.5, for example, it tells you that that linear relationship itself doesn't exist, because you run the linear regression, you come up with some sort of a hyperplane, but this score is, this number is pretty high, and therefore R square is a little bit low. It's 1 minus this thing, and therefore, probably a linear relationship doesn't exist at all. So, I want to sort of recap this once again, because this is important. R square score is it serves multiple purposes. Firstly, it tells you how good a job your linear regression model is doing. Okay, it sort of is the percentage, okay, of the response variable variation that is explained by the linear model. Okay, so how much of a difference there is between just using an average versus using a linear regression. That is what is captured by the R-square score. And finally, another way of looking at it is that assuming you run your linear regression correctly, which you will, the R-square score also tells you whether a linear relationship exists at all between the observed variables and the independent variables. So that is what the R-square score does for you. Okay, just want to throw out one more definition. There is something called the adjusted R-square score, and let's see what this is and the reason why you need something like this. Now, coming back to the R-square score, what you will observe over here is that this equation does not rely on n, which is the number of independent variables, right? So you may create a model that has 3 independent variables and gives a R-square score of, let's say, 0.7. Okay, and then you move on to increase the number of independent variables to 30, and your R-square score becomes, let's say, 0.72. Okay, now here you have significantly increased the number of independent variables, but the increase in your R-square score is relatively less, right? So therefore you have to ask the question, is it worthwhile adding these 27 additional independent variables to get this marginal improvement in the R2 score, right? So what you would actually like is a measure that not only looks at how well your linear model captures the variation in your training data, but somewhere that R2 score should also factor in the cost of doing that. In other words, how many independent variables did you need to come up with your model? That is exactly what the adjusted R-square score does. And in R-square, the adjusted R-square is really, this is the formula. Okay, just keep that in mind. I'm throwing it out here. It is 1 minus, in the numerator, 1 minus R square multiplied by m minus 1, in the denominator m minus n minus 1. Here m is the number of observations, the number of points in your training data, and n is the number of independent variables. Okay, so as n increases, your R square will go down, right? Because if n increases, this reduces. If this reduces, this increases. And if this increases, your 1 minus this reduces. So it puts a penalty on using more independent variables. So that's what the adjusted R square score is. I just wanted to put this definition out there. The R square score is, by the way, going to come in handy subsequently. So it's important to understand what it's doing, right? The improvement over using the straight off average, right? That's one interpretation of R square score. The other interpretation of the R square score is an indicator of whether a linear relationship exists at all between the observed variable and the independent variables, right? So let's keep that in mind. Assumptions. Let us now look at the assumptions we are making with respect to the underlying data while we go about doing our linear regression. Okay, so assumptions pertain to the data. The first assumption is the assumption of linearity, of course, right? And the assumption of linearity is basically, it says that the dependent variable has a roughly linear relationship with each of the independent variables, right? So the independent variables, you have a bunch of independent variables and you have a dependent variable in your training data. And you assume essentially that the dependent variable has a linear relationship roughly with each of the independent variables. Why do I say roughly? Because you are never going to get an exact linear relationship. These are observations usually of physical processes, and therefore what you're looking for is a roughly linear relationship, right? Why does this assumption, what is important about this assumption? I mean, here you have a linear model. In linear regression, your objective is to create a linear model whereby the dependent variable is a linear combination of the independent variables, right? So the dependent variable has a linear relationship with each of x1, x2, x3, xn and so on and so forth, right? That's your model. Now, if your underlying data, if your observed data did not have such a linear relationship, the behavior of the training data would not be modeled by a linear model, right? So if your underlying data did not have a linear relationship between the dependent variable and the independent variables, naturally a linear model would not be able to replicate that behavior of the training data, which is what we want to do with linear regression. So therefore, this assumption is absolutely necessary. It's important. Okay. So the assumption of linearity is the first assumption you are making when it comes to the data that you're trying to model. Okay. Now, how do you measure the extent of a linear relationship, right? I mean, you could plot graphs like these. I mean, for example, you could plot one of the x over here and the y over here. So this is the dependent variable, and you could sort of on the x-axis pick any independent variable and sort of do this exercise for each of the independent variables and see what the graph looks like. Okay. So this is an example of, for example, that you could see in one of the graphs. This could be another graph. This could be a third graph and so on. Now in each of these graphs on the x-axis, you have one of the independent variables, and on the y-axis, you have the dependent variable. Right? Now, this looks like a roughly linear relationship. I mean, you can see it with your eyes. This clearly is not a linear relationship. I mean, it's all over the place. This again is a linear relationship, of course, with a negative slope, right? So visually, you can look at these graphs and you can say what's a linear relationship and what is not a linear relationship. These kind of graphs are known as scatter plots. Okay, scatter plots. Okay. So this visual inspection is a good thing, and you could sort of make your decisions based on these. But what if you wanted to formalize this a little bit more and you wanted to come up with a numerical measure of the linear relationship, numerical measure of the extent of the linear relationship? So for example, if I had some additional points here, okay, is that still a linear relationship? When does it stop being a linear relationship? And what is a greater linear relationship? And what is a lesser linear relationship? So clearly, I mean, since we are talking about algorithms and so on and so forth, we need a numerical metric to measure the extent of linear relationship. That is done by something called the Pearson correlation coefficient. Okay, the Pearson correlation coefficient, which is defined with this equation. The Pearson correlation coefficient R is given by this formula right here. Okay, this measures the linear correlationship between two data sets. Here, let's say data set X and data set Y. These are two data sets. Xi are the elements of the data set X. Yi are the corresponding elements of data set Y. Okay, so if we say that we have m points in our training data, I would go from 1 to m, right? If we were dealing with our training data. Right? X bar is the average of Xi. Similarly, Y bar is the average of the Yi, calculated from 1 to m, right? So this is the formula for Pearson correlation coefficient, and it finds the correlation between two sets of data. Like I said, it measures the extent of linear relationship between two data sets. However, it does not capture non-linear relationships or non-linear correlations. Okay, So if yi was xi square, you would not get a high Pearson correlation coefficient. Okay. So Pearson correlation coefficient should, actually be called Pearson linear. Okay. This is implicit. Pearson linear correlation coefficient, because it measures the linear correlation. Okay. If you examine this equation, R takes values from -1 to 1. Okay. So R takes values from -1 to 1. Typically, a value of R, magnitude of R higher than 0.8 is considered to be a high linear correlation. Between, let's say, 0.8 and 0.45, you would consider it to be moderate level of linear correlation. 0.45 to 0.025, let's say, would be weak. And under 0.25, if your value of the magnitude of R is less than 0.25, you would consider that as, the two data sets not having a linear relationship. Now, these values are, this table that I have shown you here are approximate values. Of course, it depends upon the problem that you are trying to solve in terms of what is acceptable to you for that particular problem, what's not acceptable, and so on and so forth. But broadly speaking, these are the values of R, going from -1 to 1, and this is how you would define high, moderate, and weak linear relationship based on the value of computed R. Okay. So, for example, in a graph like this one, you could perhaps end up with a R of 0.85. In a graph like this one, second one, you would probably end up with an R of 0.03. And for this one, where there is a negative correlation, you could probably end up with a value of -0.83, for example, let's say, right? Because these things are pretty linear, but it's a negative slope, and therefore you have a negative sign of R. Okay. So that's what the Pearson correlation coefficient does. It measures the extent of linear relationship between two data sets. Okay. And these are what the values of R indicate. Now, I don't really like to throw formulas at you without, sort of digging deeper and trying to make sense out of these formulas. Okay, so let's examine this formula in slightly greater detail. Okay, so let's see what this thing is saying. This thing in the numerator, if you considered x and y as vectors, this thing in the numerator looks like a dot product. Okay, and in a way you could say that a computation like this sort of measures the alignment between two data sets, right? Just as a dot product measures the alignment between two vectors. Okay, but there is another way of looking at this. Consider you have two data sets, okay. Let's say the data set X has data elements 2, 3, 4, and 5, let's say, okay, and Y has, let's say, Y has elements 9, let's say 1, 7, and 3. Okay. Now, if you had to multiply the elements of these two data sets, okay, and add everything up together, what would maximize that result? The sequence of these values of data sets that would maximize that product would be if you multiplied the largest term in the first data set with the largest term in the second data set, the second largest in the first data set with the second largest in the second data set, and so on and so forth, right? You can actually prove this with using mathematical induction, for example. But the value of the product, the value of the dot product in a way is maximized if the elements of X and Y are aligned in terms of their ascending and descending orders. Okay. In other words, the way to look at it is that this product, this dot product, so to speak, between x and y is maximized if both the data sets are either ascending or descending, or at least if the highest values are associated with each other and the lowest values are associated with each other, and so on and so forth, which is exactly what that linear relationship would indicate, right? So therefore this thing is a measure of, how correlated or how linearly correlated the two data sets are. Now you will ask, why is this average being subtracted? Okay. That is to ensure that a negative correlation, which is also a type of correlation, is properly captured. You don't want a situation where the value of R is close to 0 for negative correlation. So therefore what you do is, if you subtract the averages from the point in the data sets, from each point in the data set, you would end up with a high magnitude negative sign R for negatively correlated data points. So negatively correlated data points would be, for example, if the smallest value of in x corresponds to the largest value in y, and so on and so forth, right? So this is what the Pearson correlation coefficient does. And of course, I mean, the denominator, if you're wondering what's the denominator doing, it's just scaling. I mean, it's sort of measuring the magnitudes of the two data sets and dividing it, because you don't want a scenario where, the correlation between x and y increases by a factor of 10 instead of instead of 2, 3, 4 and 5, you took 20, 30, 40 and 50, right? The correlation should remain the same. So therefore you have the denominator which scales the R. Okay. So with this formula, the value of R is going to stay between -1 and 1, with magnitude of R indicating the level of linear correlation. Okay. Let's move on to the next assumption. The next assumption has to do with something called multicollinearity. Okay, multicollinearity. And the assumption is that there is no multicollinearity. And what that means is that the values of the independent variables should not be linearly correlated. So what are we saying here? Remember, this is how we modeled the input-output for linear regression, right? We said that the dependent variable was going to be a linear combination of the independent variables, right? Our first assumption was that the dependent variable should be linearly correlated with each of the independent variables, right? So a linear relationship should exist between y and each of the x's. That was the first assumption. The second assumption says that a linear relationship should not exist among the various x's. Okay, so the independent variable should not be linearly correlated. That's what the second assumption says. So x1 should not be linearly related to x2, x3 should not be linearly related to xn, and so on and so forth. There should be no linear correlation between the independent variables. That's what this second assumption says. Okay. How do we measure the correlation between independent variables? Well, we have the Pearson formula, right? We can compute the R. For each pair of independent variables. So for example, if x1, x2, x3, x4 were your independent variables, for each of these pairs, you can find the value of R. So each of these pairs represents a data set, right? Again, in the training data, you had a number of points in the training data. For each point in the training data, you have the values of x, x1, x2, x3, x4, etc. for first training point, x1, x2, x3, x4 in the second training point, so on and so forth. So you actually have data sets x1, x2, x3, x4 when seen across all the points in the training data, right? And what you are being asked to do here is compute the value of R by taking each pair of independent variables at a time. Okay, so let's say you got a value of R equal to 0.21 when your two data sets being used to compute this R were data sets x1 and x2. Similarly, you got 0.87 when you did the same exercise between x1 and x3 and so on and so forth, right? This is going to be a symmetric matrix. It's called the correlation matrix. Okay, so this matrix is called the correlation matrix because it sort of captures in a matrix form the correlations, the linear correlations between the independent variables. And it's a symmetric matrix because the correlation between x1 and x2 is the same as the correlationship between x2 and x1. Okay, in this formula, x and y are interchangeable, right? So therefore, this is a symmetric matrix. I have only drawn half of it. And each data set has a correlation of 1 with itself, which is why the diagonal is all ones. Okay. So you could do this for each pair. You could do this for each pair in the training data. Okay, in the training data, come up with this matrix and ensure that each cell is less than, for example, 0.25, right? Magnitude is less than 0.25. Now, if you observe something like entries like these, you would say that there is a high correlation between x1 and x3, or there is a high correlation between x2 and x3, and therefore the assumption of multicollinearity is not being satisfied. Okay, so you would want all the elements in this correlation matrix to be typically less than 0.25 in magnitude. So that's one way of doing things. But there is more. What if there is a linear correlation between a variable and multiple other variables taken together? Okay. Now this is going to be tricky. Okay. What if there is a correlation between a variable and multiple other variables taken together? So for example, what I am saying is, what if, let's say the value of R between x2 and x4, let's say, right, is less than 0.25. The value of R between x2 and x7 is less than 0.25. And the value of R between x2 and x9, let's say, is less than 0.25. And yet, x2 equal to alpha 4 x4 plus alpha 7 x7 plus alpha 9 x9 is broadly obeyed. Okay, is broadly obeyed. Now you may wonder how this can happen. I mean, for this statement to be true, would not there be a linear relationship between x2 and x4? You would ask this question, right? Well, we are talking about real life data, and your observations, your value of R that you compute is going to be computed from your training data, from what you observed, right? And it may not capture that linear relationship to the extent it should have, right? So you may not find a high R between x2 and x4 or between any of these pairs, but you may notice that this relationship, where x2 is a linear combination of x4, x7 and x9, is broadly being satisfied. This can happen in real data, right? What if this happens? In case you are still not sure, I mean, let me leave it as an exercise. I'll list this as an exercise. Why don't you create data sets x2, x4, x7 and x9 such that the pairwise Pearson has small values, but this equation for some values of constant x4, alpha 4, alpha 7 and alpha 9, this equation is broadly satisfied. Why don't you manufacture a data set for which that is true? This is what brings us to something called variance inflating factors. Okay. Let us see what variance inflating factors are. We had this linear model. Again, I just write it down for reference. Y equal to W1, X1, etc. What you want to do to check that what I just said in the earlier slide is not happening, okay, is to run regressions assuming each independent variable is a dependent variable, while other independent variables continue to be treated as independent variables. Okay, so this requires a little bit of attention. So let's go over it once again. Here in our model, this is our linear regression model that we have been concerned with. Y is the dependent variable and x1, x2, x3, x up to xn are the independent variables, right? Now we want to make sure that the scenario that we discussed in the earlier slide, where there is a sort of a linear dependency between x2 and x4, x7, x9 taken together, is not happening. How do we find out that that is not happening? Or how do we find out if that is happening, right? To do that, what we are going to do is we are going to run regressions assuming each independent variable is treated as a dependent variable, while the other independent variables continue to be treated as independent variables. So what you try to do is you try to write x1 in terms of all the other x's, then try to write x2 in terms of other x's, and so on and so forth. Okay, so let's do that. What you want to do is you want to create a model where you are trying to write x1 in terms of x2, x3, xn and so on and so forth. So you run a regression. What does running a regression mean? It means treating some variables as independent variables, treating one variable as a dependent variable, and trying to come up with these constants w's so that this relationship broadly holds on that data set. That is the meaning of running a regression. Okay, so you first run the regression and try to write x1 essentially in terms of x2, x3, xn and so on and so forth. Okay, where w1, these w's are some constants, right? And after you run this regression, you find the R-square score for that regression. Okay, you find the R-square score for this regression. Okay, to remind ourselves, what's the R-square score? R-square score is this. Okay, remember when we talked about the R-square score, I said that the R-square score, while you are engaged in the process of finding your best hyperplane, your R-square score tells you how good a particular hyperplane is. After you have determined your best hyperplane, after you have run the regression, the R-square score becomes really an indicator of how linear your data really is. Okay, how close to the hyperplane are your training data points. Okay, so after the regression is done, the R-square score actually measures the level of linearity between the dependent variable and the independent variables, right? So R square 1 for this regression tells you if x1 is really expressible as a linear combination of x2, x3, x4, xn and so on. Right? Then you run a linear regression similarly for x2 in terms of the remaining independent variables. So x1, x3 all the way to xn. And do this for all the x's, and until for xn you try to write xn in terms of x1, x2 so on till xn minus 1. And for each of these regressions, after you are done with the regression, you find the corresponding R square score. Okay, so you would have n values of the R square score for each of this regression, and each of these R square scores would basically tell you how much of a linear relationship existed between that independent variable and the remaining independent variables. Right? Okay. This is what you have to do. The variance inflating factor for the independent variable j is defined as 1 over 1 minus r square j. So for the jth regression, you had r square j, and VIFj is simply 1 over 1 minus r square j. This is the variance inflating factor. Okay. Earlier in the lecture, we said that a R square value higher than 0.8 indicates high multicollinearity for the variable j. We did not use the word multicollinearity, but we said that if R square was higher than 0.8, it was, your linear regression was successful. Successful in the sense that your training points lay relatively close to the hyperplane, right? R square greater than 0.8 translates to VIF higher than 5, right? VIF higher than 5. And if your VIF is higher than 5, that is taken to indicate a high multicollinearity for the variable j. So the jth independent variable can be written as a linear combination of the remaining independent variables. That's what this means. Okay, so let's say if R square 3 was high, it says that x3 can be written as a linear combination of x1, x2 and the remaining x's till xn, right? So that's what it means. If that happens, you don't want that. We'll come to the disadvantages, what impact multicollinearity has. But let's first understand what multicollinearity is and how we measure it. Okay, if xj has a high multicollinearity, I have written something here. If xj has high multicollinearity, the standard error of wj, the corresponding term, is high. Standard error is directly related to variance. I am trying to explain why we have this complicated name, variance inflating factors. Clearly this means something. I am trying to explain this complicated terminology here. If xj has high multicollinearity, the standard error of wj is high. Standard error is directly related to variance. This means the value of wj changes drastically based on which sample from training set is chosen. Okay, high VIFj therefore indicates that the variance of wj is inflated, and therefore the name VIF, it's called the variance inflating factor. Okay, I have just read what I wrote. Let's sort of go over it in a little bit of detail, not too much. Essentially what we are saying is, if x3 has a high multicollinearity, the value of w3 ends up having a high variance. Okay, the variance of W3 is inflated. And that is the reason for this terminology, variance inflating factor. You measure the variance inflating factor of each of these terms, and then you decide that if VIF is higher than, if any of the VIFs is higher than 5, that particular independent variable has a high multicollinearity in terms of the other independent variables. I'm not going to sort of get into the why the standard error becomes high and how it's related to variance. That's a little bit of beyond the scope of this particular lecture. It's sort of outside the focus of this particular lecture. The reason I mentioned it is that it's a reference. If any of you is interested in digging into this a little bit more, you have this information right here, and that will tell you what to search for. Okay, so we will leave it at that. We will leave it at that in terms of explaining why this name exists. But from our perspective, what we are saying, as far as we are concerned, what's important to us is VIF greater than 5 indicates a high multicollinearity, and in the next slide we are going to see what impact it has on our linear regression. Impact of multicollinearity. So we saw what multicollinearity was, we saw how to measure it. Now let's understand its impact. Multicollinearity makes it hard to interpret your coefficients. Okay, multicollinearity makes it hard to interpret your coefficients. What that means is, you remember, you go back in this lecture and see what we were talking about. We said that one of the reasons for learning for running a linear regression was to predict the value of the dependent variable on test input, on future inputs, right? Another purpose of linear regression was to sort of evaluate the relative impact of various independent variables on the dependent variable, right? So how important each of these independent variables were in terms of their impact on the dependent variable. That was the second purpose of running linear regression. Okay, that second purpose is not met when there is high multicollinearity. So if x3, for example, is dependent on is related to, in some way to x2, x7, x9 and so on and so forth, the value of W3 does not correctly capture the importance of x3. Okay, the value of x3, the value of W3, its relative magnitude does not capture the relative importance of x3. So that second purpose of running a linear regression gets defeated. Why does that happen? I mean, because like we said, if x3 is a linear combination of x2, x7 and x9, you could sort of balance out the value of W3 by modifying the values of W2, W7 and W9, right? And therefore W3, the value of W3 that you end up after running the linear regression does not correctly capture the relative importance of x3. It results in coefficients with large standard errors. Okay, that's the values of the coefficients can be vastly different based on different samples of training data. So for example, if you took different training data, right? I mean, often at times when you run AI algorithms, what you do is you have your entire training data and you sort of take subsets of the training data to repeatedly run the regressions to see if, all of them roughly converge to the same values, right? So if you had multicollinearity, the standard error of that coefficient is going to be high, which means that the value of W3 could vastly differ depending on which subset of the training data you took to run your regression. Okay, now this is sort of related to point number 1. I mean, this point and this point are sort of related. but I've just sort of put them, to re-emphasize the point. Multicollinearity is not a significant issue if the purpose is to make predictions. So if your purpose of running the regression was to do predictions and you are not really bothered about the relative importance of various independent variables, etc., multicollinearity is not a significant issue. Okay. Remediation. So what is the remedy? What is the remedy in case you observe that there is no linearity between the between the dependent variable and the independent variables, or if collinearity exists among the independent variables? How do we remediate? What is the recourse we have? Well, one recourse is, as always, transformations or working piecewise. Okay, so breaking the problem into multiple problems is called piecewise, and we looked at this earlier in an earlier lecture. Or transformations. You could transform your variables into something so that linearity gets obeyed. Okay, or multicollinearity goes away. So transformations and running piecewise are one way in which you can remediate. Not always, but these are two things that you may want to explore. If you have multicollinearity, you could actually drop variables with high multicollinearity. So like I said, if x3 had a linear relationship combined with x2, x7 and x9, you could actually just drop x3. Okay, you could drop x3 in your regression entirely, because the behavior of x3 could be captured in terms of x2, x7 and x9 in any case. So you could perhaps drop variables with high multicollinearity. That's one thing you could consider. And then there are, slightly more sophisticated regression techniques beyond plain linear regression. For example, ridge regression or lasso regression, and we will study what these are in the subsequent lecture. But there are indeed techniques that allow you to handle multicollinearity or non-linearity, in a more effective manner. So this is what your remediation would look like. Next assumption. Normality. Okay, this assumption says that the probability distribution of the residuals is normal. Okay, so what do we mean here? This, for example, is an example of a hyperplane that you got by running your linear regression, and the test points, the training points are shown by black dots here, and we know the residue is defined as the difference in the y coordinates of the black point and the corresponding point on the hyperplane, right? So these are the residues. What this assumption says is that the probability distribution of the residuals should be normal. Okay, now normal not in the colloquial sense, but assuming that you heard of something called the normal distribution, this is what the normal distribution looks like. Equation is 1 over square root 2 pi sigma square e to the power x minus mu square upon 2 sigma square. Here mu is the mean and sigma is the variance. Okay, so this is what a normal distribution looks like. Plotted a few graphs of normal distribution for various values of mu and sigma, and you can see what it looks like. The assumption says that the residues, I mean, if you take the probability distribution of the residues, they would reveal a normal probability distribution, meaning a probability distribution that sort of satisfies this equation. That is what the normality assumption is. Probability distribution of the residuals computed after your regression is done, the probability distribution is normal. Okay, so what's the big deal? I mean, why should the probability distribution of the residues be the normal distribution? Well, the normal distribution is special. Okay, the normal distribution is special because it often describes the actual distribution of the random errors in real world processes. Okay, so for example, the distribution of height of males is a normal distribution. The weight of babies at birth has a normal distribution, so on and so forth. And this is an observation. What it says is that if you were to look at what you would consider a real world random process, its distribution is likely to be normal. Okay. So what we are effectively saying by insisting that the distribution of residues be normal, what we are saying is that we have successfully extracted all the patterns that existed in the data, okay, or captured every pattern that existed in the data, and now what remains of the residues is truly random. That's sort of, the underlying idea. The normal distribution often describes the actual distribution of random errors in real world, and therefore if you end up in a situation where your residues have a normal distribution, you can assume that they are truly random. You can no longer, extract anything further from them. You are done. And therefore that is the assumption that we work under. If your distribution of residues is not normal, there is probably, something more you can do with your model to sort of make it better. That's the logic. So what is the remediation if you see that the residues do not have a normal distribution? The remediation is to see if any independent variables have been overlooked. Okay, so like I said, if your residues were truly random, it means that they have no pattern in them. But if they are not perfectly random, there probably is some pattern to them, and that pattern can possibly happen if you have overlooked some independent variables. So you have to expand the scope of your solution and see if there are any independent variables that you have missed capturing. Next assumption. This assumption is the assumption of homoscedasticity. Okay, and what this assumption says is that the variance of residual should be constant irrespective of the values of the independent variables. Okay, so the variance of residuals should not change based on the values of independent variables. Let me sort of try to show this in a graphical way. So if this was your independent variable along the x-axis, okay, and this was your dependent variable, and if this was the plot of your residues, note that, don't look for linearity, etc. over here. This is not y versus x. Sorry, this is actually not y. This is the residues, right? The residues. Sorry about this error. This is the residue. Let me residue. Okay. So these are the residues, and as you can see, the variance of these residues actually remains the same irrespective of the value of x. Okay, irrespective of the value of the independent variable. In this graph, however, if you plotted the residue versus x, you can see that the variance goes up. The variance increases as the value of x increases. So here it was less, and here it increased as the value of x increased. So this does not satisfy homoscedasticity, whereas this does. So this is the kind of this is the kind of behavior you want to see for your residues, and you do not want to see this type of behavior, right? So that is homoscedasticity. The remediation for this is to experiment with transformations of that independent variable. So you may want to engage in an exercise where you see if you can transform the independent variable so that the variance of residues stays constant. Okay, that would be the remediation. Again, I mean, what's happening in cases like these is that there is probably some behavior that you have not captured, okay, some behavior that you have not captured, and therefore a transformation or, the way that independent variable influences your dependent variable is a little bit different, and therefore transformations are the solution to situations like these. What I want to do next is take a real life example and see how we could possibly apply linear regression to solving that problem. Okay. So here is the example we are going to consider. We are going to try and create a linear regression model to predict sales of mobile phone models based on various factors. Okay, so there are numerous mobile phone models in the market, and suppose you are you owned a mobile shop. You wanted to create a linear regression model to predict how many pieces of a particular model you would sell based on various factors. Okay, so let's say you began by gathering some training data that looked like this. Okay, so the variable that you were interested in monitoring was, let's say, sales per week. Okay, sales per week, and I'm going to sort of use rupees as my currency, and what I indicate over here is this means that this is in terms of 6.5 thousand per week. Okay, so this indicates 1,000 and so on and so forth for all parameters. Sales per week is what I want to monitor, and my independent variables are the variables that I have sort of tabulated over here, right? So how many months ago was the model launched, the price of the model, the discount I am offering, the marketing budget I have set aside, the social media budget, maybe TV ads, the battery life of the model, screen size. I mean, these are parameters of the model itself, whereas these are some of the sales and marketing related parameters. And then maybe, rating on, let's say, Amazon or other portals given to that particular model, right? So this is what my training data would typically look like. The sales is the dependent variable. I'll repeat, the sales per week is the dependent variable that I'm interested in, and these are the independent variables, numerous independent variables, and each row is basically one point in the training data, and you could have potentially m of these, right? I mean, thousands of sample points. Okay, so let us see, for example, how we would approach the problem. Now, clearly there are multiple ways of approaching this problem, and different people may do different things, and not all, there is not necessarily one way which is the correct way and so on and so forth. I mean, typically when you're solving problems like these, you end up in situations where you have to iterate. My purpose is to essentially show you one way of approaching a problem like this. Okay, so let's list out the sample steps we would go through in coming up with a good linear regression model. Okay. The first thing to do, of course, is to gather adequate training data, right? Gather adequate training data. Now, you may wonder what adequate training data means. I mean, how much is adequate? And we'd sort of touched upon this earlier in this lecture and the previous lecture. But let us say for now, let us just say that if you had n independent variables, your m should be, let's say, greater than 10 times n. Okay, so if you were monitoring 10 parameters, for example, you would probably need at least 100 points in your training data. So that's a, let's say for now, let's use that as a thumb rule for how much would be training, adequate training data to start with. The second thing you would do is you would scale the units of measurement. Okay, what do I mean? Let's go back. In this slide, I have sort of mentioned the units for each independent variable. So when was this model launched? How many months ago? Okay, I'm calculating this variable in terms of months. The price I'm tabulating in terms of thousands of rupees. The discount I'm offering is tabulated in terms of hundreds of rupees. My marketing budget I am tabulating in terms of lakhs of rupees, and so on and so forth. Why am I doing that? I am doing that so that the numerical values in each of the columns, are roughly in the same dynamic range. So over here, to make matters simple, I have said that they are, let's say, from 0 to 10. I mean, if in this case there are no negative values, but even if there were negative values, their magnitudes would go from, let's say, -1 to -10. I mean, I'm trying to keep all the variable values in the same, in roughly the same range. And I can do that by selecting a suitable unit for each of the independent variables. Okay. Now, for example, for battery hours, this does not fit into what I said. I mean, these values look distinctly different. And maybe instead of hours, I could have measured battery life in terms of, units of like 3 hours each. So in that case, each of these would get divided by 3. That would be the sensible thing to do over here. Right? Screen size in inches, that's another independent variable I have considered. Rating typically goes from 1 to 5 and so on and so forth. So if the values of the independent variables have different dynamic ranges, I mean, some of the numerical values runs in thousands or millions, another value runs numerically from 0 to 10. You want to scale the values so that, or choose the correct units for each of the independent variables so that all the values are roughly of the same numerical size. That's what I meant. That's the first thing you do. That's scaling, units of measurement. The next thing you would do is just run a regression and find the R2 score. Okay, so when I say run the regression, you know exactly what I'm talking about. You could go with either of the two approaches. You could either use the normal equations which give you the closed form values of W, or you could do this iteratively. If you had lots and lots of independent variables, you could use the gradient descent approach and come up with the best values of W. And after you come up with the best values of W, you would find the R2 score for your linear regression. Why do we do this upfront? I mean, before we do anything else, why do I prefer to do this upfront? Because it tells you what your starting point is, right? So without some of the other operations that you could subsequently carry out, what's your starting point in terms of the R2 score? How good is your linear regression if you just sort of use the data as it was? So that's like a marker you lay in the ground. That would, for example, be my third step. My next step would be to check the linearity vis-a-vis each independent variable. Okay, so when we write the linear model as y equal to w1, x1, w2, x2, etc., remember one of the assumptions that we talked about was linearity. and the dependent variable had to have a linear relationship with each of the independent variables, and that is what I would check. I would either do it using scatter plots if there weren't too many independent variables, or I would use the Pearson coefficient, right, which we've studied. So I would check the linearity vis-a-vis each independent variable. And then based on what the relationship looked like, I may want to solve the problem piecewise for certain independent variables. So for example, if you noticed, if in your scatter plot of price versus sales, you, for example, let's say you noticed behavior like this, right? I mean, something like this, etc., right? So you may perhaps say that the behavior for models that are low priced models is dramatically different than the behavior for models that are highly priced, right? So then you may want to just divide the problem and solve two separate problems, one for mobile models that are, let's say, less than 10,000 rupees, and solve another independent problem for models that are, let's say, more higher than 10,000 rupees. So this is called piecewise, and you break the problem into two parts if you see this kind of a behavior on any particular independent variable. You could also look at transformations, right? Like I said, I mean, if you see a quadratic type of a behavior, instead of using xi as an independent variable, you could use xi square as the independent variable, so that you have a linear relationship. So some sort of transformations can also be considered, and this is the place to consider those transformations. And for item 5 and 6, the scatter plot would give you better insight than just taking the numerical Pearson coefficient. Okay, so it's better to go with scatter plots if you want to consider doing piecewise, or if you want to consider transformations, because these plots give you a visual indication of what exactly is happening. Those would be my next steps. At this point in time, I would probably run the linear regression once again. And check my R square. Okay, check my R square again and see if I have made any difference vis-a-vis the R square that I calculated right in the beginning. And my new R square would probably tell me how much of progress I have made by, doing the piecewise stuff or doing these transformations. So by addressing the issue of linearity, how much improvement did I bring to my R square is what I would look at while I am over here. The next thing I would probably do is look at my residue distribution. You remember the assumptions we talked about in terms of normality of residue and so on and so forth. So I would look at the residue distribution, see if it is close to normal. If it is not close to normal, I would probably investigate if there are more independent variables that need to be considered. So have I missed out any independent variables that have an impact on the sales of a mobile model, right? So if my residue distribution was not normal, this is something I would definitely investigate. The next thing I would do is determine multicollinearity. Okay. Now, remember when we discussed multicollinearity, we said that per se it does not affect the quality of your predictions. But in real life, it is always a good idea to drop some of the variables if the VIF is very large. For example, if VIF is greater than 10, you may be better off simply dropping those variables. Okay. Having done that, I would run regressions and check R square with multiple 80-20 distributions. So what are these 80-20 distributions? Let's say if I have 1000 points in my training data, I would randomly divide into 800 for training, 200 for testing, and run a regression on the 800, run the testing on the remaining 200, see what my R square was, see what my accuracy was, and I would sort of keep an eye on two things. Number one, if I were to do it with different data sets in 80-20 proportion, I would like my accuracy to more or less stay constant. I would like my R square to more or less stay constant. Okay. So I would see if that is the case. And if that is indeed the case, I would probably say that I have converged. Okay. So these are some of the sample steps I would go through in if I were to be confronted with a problem like this one, right? I'm just going back. If I were to be confronted with a problem of having to create a good linear regression model to predict the sales of mobile phone models, these are the steps I would follow. Now, these are not hard and fast rules. I want to clarify once again. This is one way of approaching the problem. What I want to emphasize is that your approach to the solution is probably going to be iterative. You're probably going to have to keep an eye on your R square score and your accuracy with every modification and every tuning that you do. Okay, so that is the important point, but these are some of the steps that you would go through to come up with your eventual solution. I have used the words run a regression several times, in the last 10-15 minutes. And since we are dealing with a real life example, I want to show you some Python code for linear regression. Now, the world has changed. Okay, in the last couple of years, 2-3 years, the world has changed. And I'm not going to show you Python code that I write. Okay, my favorite way of generating code is to simply use ChatGPT. Okay? And I'm in any case going through this exercise to show you how, in a way, how ridiculous it is. So I went to ChatGPT and typed in, give me Python code to run linear regression on data with 10 independent variables. This was my prompt. Okay. That's all I did. And within seconds, I got what I was looking for. What I've done here is actually taken a few screenshots and put them up on screen here. And it does a pretty good job. I mean, as you can see, it allows you to even copy the code if you want to paste it into a Jupyter notebook and so on and so forth. It uses the library sklearn. The code is fairly well documented. It tells you what it's doing. Generate a synthetic data set, then convert into a data frame, split into training and test sets. Create a model. I mean, see how easy it is. Everything that we learned, all the theory that we did is just in these two lines, right? And then you can make predictions on the test data. And it also finds the mean square error, the R2 score, etc. for you if you want. And it finally prints the model coefficients, which are the W's, right? So, and right at the end, it also actually gave me a helpful explanation for what it had done, and said that, I like this line at the end, you can replace the synthetic data generation with your actual data set as needed. So, in case you were wondering, how do I run this on my own data set, it tells you what to do. So it's fairly simple now for somebody to generate code for these algorithms that we are talking about. And the reason that I went over this exercise was to make an important point. I mean, we spent the last 4 hours talking about linear regression, 4 hours, right? And it did not take us 4 seconds to come up with the code. There was a time when people learned about algorithms so that they could write good code, right? That time has passed. Now everybody can write code of equal quality, and ChatGPT will do it for you. The focus has shifted really from writing the code to understanding the theory underlying what we are doing, solving the problem, taking the right steps taking the right approach to solving a problem and so on and so forth, which is what we spend most of our time on, right? Although you have this code at your fingertips, it still is extremely important to understand what's happening underneath so that you can fine-tune your approach to solving the problem, right? So that has been the focus of our lecture as well. We have spent a few seconds on the Python code, and we've spent 4 hours on discussing the underlying theory, the assumptions, the what's happening, so on and so forth, right? Okay. I want to end this lecture with a few questions. Okay, I had a few questions in my earlier lecture as well, and these questions are for those among you who are a little bit more thoughtful. And if you thought about these questions, I mean, don't go to ChatGPT. We just saw ChatGPT. Don't go to ChatGPT for answers to these questions. If you spent a few minutes investigating the answers to or thinking about the answers to these questions, it would undoubtedly improve your understanding of linear regression. So I have a few questions. Okay, this was our linear regression model. My first question or assignment is to ask you to create a data set that shows overall linearity but not individual linearity. So I want to make a point here. You remember when we talked about assumptions, our linearity assumption said that y, your dependent variable, was linearly related to each of these independent variables. So y and xj had a linear relationship for all j's separately, independently, right? So that was our linearity assumption. Now, some of you may be wondering that if I'm going to create a model like this, is it possible for me to satisfy this? Is it possible for me to have data that satisfies this model without each individual linearity assumption being satisfied? Okay. So that is a question that some of you may have had. I certainly had that question. And that is what I'm asking you to do. I'm asking you to create a data set showing which satisfies this overall equation, but y is not linearly related to x1, or y is not related linearly to x2, and so on and so forth. Okay. So that is the question. My next question. We looked at something called the adjusted R square score, right? And it was related to the R square score in this way. And if you go back several slides, we also discussed why do we need an adjusted R square score? Why is R square score not enough? And in a nutshell, the reason was that R square does not capture the penalty on n, the number of independent variables, whereas adjusted R square score does that. Okay. Now this is the formula for adjusted R square, and when I looked at this adjusted R square score for the first time, I remember thinking that there was something odd about this formula. So if you would like to pause this video for a moment and look for yourselves what's a little bit odd about this formula, stop the video here. I'll give you a second and then I'll tell you the answer to this question. Okay, what struck me as a little bit odd was the fact that m and n appeared together in this equation. Okay, now remember, m is the number of observations, which is the number of training points, and n is the number of independent variables, right? So these are, I mean, to my mind, these were always, apples and oranges, because you could have 1,000 observations, 1,000,000 observations, whereas you may actually have, let's say, 5, 10, 15 independent variables, whatever. I mean, these were not in any way related in our mind so far, right? So can you really add apples and oranges? I mean, that is what struck me as odd. In fact, if you sort of put values for some of these variables, if you put values of m as 1 million and put value of n as, let's say, 22, and then see how n going from 22 to 25 affects the R square score, and then do the same exercise for m being equal to, let's say, 500 instead of a million, you will see that the impact on R square score is not exactly similar. And therefore, it did strike me as odd that we were sort of adding apples and oranges over here. So that's what I thought. If any of you have other thoughts, or if you do not think this is a little bit odd, please put in the comments to this video. But that's my second question. Third question is relatively simple. What is the likely mu? What is the mean for the normal distribution of residuals in linear regression solution? This is a relatively simple question. Question 4. We talked about homoscedasticity as one of the assumptions, and remember it pertained to the variance of the residue not changing with changing values of the variable, right? That is what it was. Now, there are numerous real life examples where data is heteroscedastic. That means not homoscedastic. And I want you to think of 2 examples in real life that are heteroscedastic in nature. Okay, so natural examples. I don't want you to construct data. I want you to think of real life data examples. That's question number 4. Question 5. This is a little bit of an interesting one. You know, the linear regression problem in a way can be thought of as a curve fitting problem, right? You're fitting a curve into your data. The curve is actually a linear straight line or a hyperplane. In 2 dimensions, it's a straight line. In multiple dimensions, it's a hyperplane. But you're trying to find the best hyperplane that fits the data. So in a way, it's like a curve fitting problem. Okay. My question to you is, can you come up with your own mechanisms, maybe even simple mechanisms, to do some sort of a curve fitting on your training data, which you can then use for predictions, okay, and compare your answers with those of standard linear regression. So what this would entail is you to create a training data set and run linear regression on it, find R square score or find the mean square error, and then come up with your own mechanism, not linear regression. You could fit any sort of a curve into that data. Try to think of very simple mechanisms, I mean nothing complex, and then compare the accuracy of your model with the accuracy of linear regression. I have done that. I had a few ideas myself on how I could come up with some simple mechanisms. It depends how well they work. It's highly dependent upon the training data you have. But it's an interesting exercise to go through because it will reinforce your understanding of what linear regression actually does. Developing your own mechanisms or alternative models. Okay. This brings us to the end of our lectures on linear regression, and I want to summarize this lecture for you. This is what we did, okay? We began this lecture by looking at the stochastic and batch gradient approaches in vector notation. So we already had discussed what stochastic and batch was for the binary classification problem, but over here we looked at them. We looked at how they morph using the vector notation. Okay, so we looked at the vector notation. We then defined a few metrics to evaluate the efficacy of our linear regression. In particular, we used the R square score. We looked at R square score. We looked at the Pearson coefficient. We looked at the VIF, variance inflation factors, and so on and so forth. So these were some of the metrics that we defined. We also looked at several assumptions on the data. Now, these assumptions are assumptions in the sense, when does linear regression work well? What are the characteristics of the data that yield good linear regression models, right? So that's what we looked at. We looked at linearity, multicollinearity, normality, so on and so forth. But we spent considerable time on that. And finally, we've wrapped up this lecture with a real life example, and I gave you one way in which perhaps you could approach this problem. Okay, how you could work on it iteratively to enhance the accuracy of your model, how you could examine the data, how you could apply some of the things that we have learned in this lecture, and so on and so forth, to come up with a model that gave you a better R-square score. Right? And by no means is that the only way of approaching the problem. There could be many ways of approaching the problem, but I gave you one example of how I would go about doing it. So that's the last thing that we did in this lecture. So that's it for this lecture. I will see you next time. Goodbye.